Section 5.5, we're going to start integrating in cylindrical and spherical coordinates. So when you integrate in cylindrical, any function, you're going to use the volume element r dz dr d theta. So if you just want to find the volume of a solid, instead of integrating 1, you integrate r dz dr d theta. And in spherical, you integrate rho squared sine phi d rho d phi d theta. If you want to find the volume in rectangular, you're just going to use the volume element dz dy dx. Okay, so I'm going to do one example of volume in cylindrical and one example of volume in spherical. And then I'm just going to do two setups with you, same shape, but we're going to use all three coordinate systems. And it's just set up because I think the real challenge is the setup. Okay, so let's start. I've already set up the integral here for the volume of this solid, but I want to show you how I got the limits. The solid is bound on the sides by the cylinder and on top by the sphere. So you want to imagine a vertical line, and the vertical line enters the solid at the r theta plane, which is z equals 0. It leaves the solid on this spherical cap. Now that's the cap r squared plus z squared equals 25, because x squared plus y squared is r squared. Solve for z, and we want the top, so we're going to take positive square root of 25 minus r squared. So that's how I got these limits from 0 to the square root of 25 minus r squared. My integrand is the volume element. Now how did I get these limits? Well, if we look in the r theta plane, we're going to have those vertical lines going through the solid for all the r's and thetas within this circle that is defined by the cylinder, x squared plus y squared equals 4. So that's r squared equals 4, which is r equals 2. So that circle in the r theta plane is simply r equals 2. And so we're going to have r going from 0 to 2. And since we want to go all the way around the circle, we're going to have theta going from 0 to 2 pi. And that's how I got all those limits. All right, the first integral I did for us, because it's simple, I didn't want to waste time. We're just integrating r with respect to z, which is rz. And then I plugged in my limits, and I got that. I'm using the numbering system, which you have to do. So this is integral 1. Integral 2 is the answer from integral 1 with these limits, 0 to 2, and the differential dr. Okay, so looking at that, I think, well, that's a u sub. U equals 25 minus r squared. Du is negative 2r dr. I have r dr, so I'm going to multiply both sides by negative 1/2. So this is going to be the integral. Put the negative 1/2 out front. U to the 1/2 du. Let's change our limits. When r is 0, u is 25. And when r is 2, 2 squared is 4, 25 minus 4 is 21. Okay, so you don't have to do this, but I'm going to make this positive and flip my limit so that the lower limit is on the bottom. Again, that's a total optional step. You don't have to do it. And so now I'm going to integrate. So this will give me 1/3 u to the 3/2 between 25 and 21. So this is not going to be pretty. 1/3 and then 25 to the 3/2 minus 21 to the 3/2. Now I could simplify 25 to the 3/2 because the square root of 25 is 5. And 5 cubed is 125. So I could clean that up, but I can't clean this one up, so I'm just going to leave the whole thing. What's the point? Okay, so integral 3, we're going to go from 0 to 2 pi, 1/3, 25 to the 3/2 minus 21 to the 3/2 d theta. All right, that's all just constant with respect to theta. So that's going to be theta times all that stuff between the two limits, 0 and 2 pi. There's going to be 2 pi times this number. So I'll have 2 pi over 3, and then 25 to the 3/2 minus 21 to the 3/2. There we go. There's our volume. Next one. Again, I've done the setup, but I'm going to explain to you how I did it. Find the volume of this, I don't know, it looks kind of like a lifesaver with an odd shaped inside. It's bound on the sides by the sphere, rho equal 2, and above by the cone, and you're only seeing part of the cone here, phi equals pi over 3. So let me explain. my volume element is rho squared sine phi d rho d phi d theta, so I put that in. When I do spherical coordinates, I want to imagine a line that starts at the origin and emanates out, and the surface that that ray begins on is your lower limit. Now, the solid is actually goes all the way to the origin, so that's why I have rho starting at 0. But that line leaves my solid at this surface rho equal 2. So I've got those lines, and they start at 0, and they leave the solid at rho equal 2. So that's where I got 0 to 2. Now, where did I get these limits pi over 3 to pi over 2 for phi? For phi, you want to start up here. This is phi equals 0. Phi is the angle between the positive z-axis and the ray that you're looking at. And so my solid, if I start going down, here are my rays, my solid isn't starting yet. I'm not in the solid yet. That's why my phi is not starting at 0, because I don't have the solid going all the way up to the positive z-axis. I'm making a real mess here. My rays don't actually hit the solid until I get to that cone. That cone is phi equal pi over 3. So that's where I start, phi equals pi over 3. Now, I stop here on the r theta plane. That is the angle phi equals pi over 2. Remember, phi can only go from 0 to pi. And when phi is pi, you're down here on the negative z-axis. But I'm bound below by the xy plane, so I only want positive values of z to mix coordinate systems here. So I'm going to stop at phi equals pi over 2. Theta is easy. Go all the way around the circle to get that whole shape. All right, again, I've done the first integral for us because it's very simple. I'm integrating rho squared sine phi with respect to rho. So the integral of rho squared is 1/3 rho cubed. And I put in my limits and I get 8/3 sine phi. Again, we're doing the numbering system. My next integral is also pretty easy. I'm just going to integrate sine phi with respect to phi times 8/3. So this is 8/3 cos phi, and it's negative. And then I've got pi over 2 and pi over 3. So that's negative 8/3. Cosine of pi over 2 is 0. And then cosine of pi over 3 is 1/2. So that's going to give me positive 4/3. Integral 3, the third integral is usually pretty darn easy on all of these. Integral 3, we're going to go from 0 to 2 pi, 4/3 d theta, which is 4/3 theta between 0 and 2 pi, which gives me 8 pi over 3. There's my volume. Now, fun part, well, I think this is all fun. We're just going to do some setups. The first one is the top cap of this sphere when it's sliced by the plane z equal 2√3. The sphere is ball of radius 4 centered at the origin. So the equation for that surface is x squared plus y squared plus z squared equals r squared, which is 16. The plane I already did, just z, it's given to us, z equals 2√3. And so first of all, for the limits on z, we need to solve this for z. The top of that sphere is going to be z equal the square root of 16 minus x squared minus y squared. Okay, so we're imagining lines going up like that. They're going to enter our solid on the plane z equals 2√3, and they're going to leave on the cap of that sphere, which is z equals the square root of 16 minus x squared minus y squared. Now, for what values of x and y are those lines going to go through that top cap? Okay, so z is 2√3, and so just plug 2√3 into z here. So they meet on x squared plus y squared plus 12 equals 16. So that's x squared plus y squared equals 4. So that's the circle of radius 2, centered at the origin. Now, I could have also gotten that circle by setting z squared equal to z squared, or I could have even set z equal to z if I had set 2√3 equal to the square root of 16 minus x squared minus y squared, I would have gotten to the same circle. Okay, so now our limits on x and y. So we're going to do y next and then x. So if we're doing y, we're thinking of vertical lines going through that circle. They enter on the bottom of the circle, which is y equal to negative the square root of 4 minus x squared, and they leave on the top, which is y equal to positive the square root of 4 minus x squared. So those are my limits on y. Negative the square root of 4 minus x squared to positive the square root of 4 minus x squared. This is ugly. You wouldn't want to do this integral in rectangular coordinates, and this is why. And then for what x's do I have those lines going through that circle? Well, they start at -2 and they end at 2. So there's my setup for rectangular. Now, don't worry, because it's a lot of work to do the rectangular, but once you've done the rectangular work, the cylindrical is kind of done for you, because remember, z is z. So z equals 2 root 3 is still z equals 2 root 3. That's not going to change. What is going to change here, you can't use x and y anymore. Your sphere is z equals the square root of 16 minus r squared. And then you already know that these surfaces meet on this circle x squared plus y squared equals 4. And so that's r squared equals 4. This is the circle in the r theta plane, which is r equal 2. And so just think of this circle as r equal 2. And so now you're thinking of rays going out. So r goes from 0 to 2, and you want to go all the way around 0 to 2 pi. So to go from rectangular to cylindrical is it's a pretty quick conversion. Spherical, on the other hand, is just totally different. So the sphere, we have a ball of radius 4. That's rho equal 4. Now the plane is rho equal what? Well, in spherical coordinates, z is rho cosine phi, and that is 2 root 3. And I've explained before that a horizontal plane in spherical coordinates is going to be rho equals something times secant phi. And so solve this for rho, divide both sides by cosine, you get rho equals 2 root 3 secant phi. So that's my plane. Now we want to imagine this. I'm not going to redraw my picture, but imagine a ray starting at the origin. I'm doing the limits on rho. You're going to have a ray. Well, I can draw a new ball. It won't kill me. All right, here's my ray. It's a really crappy picture. Starting at the origin, it's going to enter the solid on that plane. So that's my lower limit on rho. It's going to be 2 root 3 secant phi. And it's going to leave the solid on the top cap, which is rho equal 4. So those are my limits on rho. For my limits on phi, okay, phi is going to start up here. I'm already in my solid on the positive z-axis, and I'll stay in the solid until I reach that value of phi where these two surfaces meet. So I have to find that value of phi. So where do these surfaces meet? Well, let's set rho equal to rho. 2 root 3 secant phi equals 4. Solve for phi. So that's secant phi equals 2 over root 3. Okay, so that's, nobody knows what that is, but if we rewrite it, take the reciprocal of both sides as cosine phi equals root 3 over 2. Now it's pretty easy. Now it's just a unit circle. Where is cosine phi equal to root 3 over 2? Pi over 6. So my limits on phi. Phi is going to start at 0. That's the positive z-axis. And it's going to go to pi over 6. All right. And then theta is easy. You want to go all the way around to get that whole cap. So 0 to 2 pi. And there's your setup. So like I said, that's a whole different animal than the cylindrical and the rectangular. Okay, let's do another one. Ice cream cone. The region bound above by the sphere and below by the cone. In rectangular coordinates, imagine a line starting, well, vertical lines, and they are going to enter the solid on the cone. And so that's, we have to solve for z. The cone is z equal to square root of x squared plus y squared. So that's our lower limit. And they're going to leave, those lines are going to leave the solid on the top half of the sphere, which is z equal square root 4 minus x squared minus y squared. So that's our upper limit. Okay, so for what values of x and y do we have those lines going through the solid? Well, we need to find out where these surfaces meet that circle and project it onto the xy plane. So I could set z equal to z, but I'm going to set z squared equal to z squared because this equation is already solved for z squared. So I'm going to set x squared plus y squared equal to, if I solve this for z squared, I get z squared is 4 minus x squared minus y squared. So that gives me 2x squared plus 2y squared equals 4, which is x squared plus y squared equals 2, which is a circle of radius root 2. All right, now I'm going to do y next. So I want to think of vertical lines. They enter on the bottom of the circle and they leave on the top. So again, just like in the previous problem, we have to solve this equation, this circle here for y, and we'll get plus or minus square root. The minus square root's the bottom of the circle, negative square root of 2 minus x squared, and the top of the circle is the positive square root, 2 minus x squared. Okay, and now x, we're going to have those vertical lines going from negative root 2 to positive root 2. Okay, cylindrical coordinates, again, it's not going to be too tough. The cone, z equals the square root, z equals the square root of x squared plus y squared, just becomes z equals r. So our lower limit is z equal r. We're going to leave on the sphere, which is, the sphere is z equal, just switch the x squared plus y squared to r squared, square root of 4 minus r squared. And we already know these guys, we want all the r's and thetas in the circle of radius root 2. So r is going to go from 0 to root 2. We want to go all the way around 0 to 2 pi. Okay, for spherical coordinates, one of the equations in your table of conversions that comes in really handy, I don't have it with me right here, but if you look in the last lecture notes on the last page, there's a whole table of conversions. This one's really helpful when you're trying to find phi. So tangent phi is r over z, and so that's going to be r over z. Well, the cone is r equals z, right? And so tangent phi is equal to 1, so phi is pi over 4. And in spherical coordinates, the sphere of radius 2 is just rho equal 2. So when you're doing your spherical coordinates, you want to think of things a little bit differently. You got, here's my ice cream cone. I've got rays emanating from the origin. They enter the solid at 0. They leave the solid on the top cap of the sphere, which is rho equal 2. So rho is going to go from 0 to 2. Then, for what phis do we have those rays going through our solid? Well, our solid goes right through the positive z-axis. So that's phi equals 0. And we're going to have those rays until we hit the edge of the cone. And the cone is defined by phi equal pi over 4. So that's where we leave. And then theta is a pretty easy one with a whole ice cream cone, 0 to 2 pi. Okay, that's it. You can see there's a lot here. This is a huge content section. So you only have, I think you have less than 10 problems on your homework, but take your time, go through it slowly. It'll pay off if you just take your time. Don't try and rush it. All right, and that's the end of this section.